Well, good morning,
Good morning,
everybody.
everybody.
Oh gosh, I'm getting an echo here. Is that taken care of?
It's fixed, Bob.
Good. Good morning, everybody. We got a 11 o'clock Central Time Zone webinar today from Alta, and I'm giving a presentation
You
on
have a
soil buffer
question or something? No, I
pH
have
methods and
questions, but
interpretations. So how many people we got on there? Because I don't want to start.
what do I do?
Corey, how many people we have on there? We frozen?
No, we're good. Sorry. We have 40
Okay.
some folks on. We're getting people still coming in. You might give it another second. Sorry,
Sure,
Bob.
I'll give everybody a little bit. So
Yeah.
I'm
God damn it.
So uh, I'm going to go ahead and get started, Corey.
Yeah, go ahead and get started, Bob. I think we're good to go.
So when we all started college, we all had that professor that had a pop quiz. So just a second, how come it isn't advancing? Oh, great.
It's okay, Bob. It's the first webinar of the year. We can have technical difficulties.
There we go. So I'm going to start the morning with the pop quiz this morning. So the focus of this is I want you to take out a piece of paper and just make notes. It's a very simple quiz, 4 questions. The first one is soil buffer pH is a measure of. Put down your answer. Second question, a factor which increases soil acidity is phosphorus fertilizer, irrigation water, ammonium-based fertilizers. Write down your answer. Pick A, B, or C. Third one, soil buffer pH and lime recommendations are based on what? And the last question is soil properties that are correlated with lower buffer pH are nitrate, soil organic matter, sand. Pick one. Write down your answers. We'll get back to that at the end of the webinar. So let's go back to the fundamentals of talking about soil pH. And so it's basically a measure of soil acidity or alkalinity. And obviously neutral is where we got an equal amount of hydrogen and equal amount of hydroxyl ions in the systems. And as we go down to the left on this graph, we go into those red zones. So we have slight acidity there between 6 and 7. We have medium between 5.5 and 6. And then we get into strong and very strong acidity. And obviously we want to maintain soils at a pH that's optimum for plant growth. And that's generally in that 6 to 6.5. Of course, unless you're growing blueberries. So soil acidity is composed of 2 primary components. There's active acidity, which is that in the soil solution, and there's reserve acidity that's associated with clay minerals. This is that acidity that's on exchange sites or it's on organic matter and really makes up that buffering capacity of the soil. So soils that tend to have high cation exchange capacity, high organic matter, are going to have a lot of reserve acidity. Conversely, soils that are sandy, low organic matter are primarily dominated by that active acidity because there's very little exchange site capacity to maintain that.
It's like how much do you want?
So where does acidity come from? Well, why do soils are acidity? That soil pH reflects the soil forming factors, be it the parent material, the climate, the topography, the biology, or the time. Any of those factors that affect that soil chemistry are probably directly related to what happens to pH. Generally speaking, parent materials are really the primary factor because parent materials, if they're from volcanic rock, they're going to be natively acid. If they're made up out of a basaltic rock or they're made up of aeolian windblown materials, they tend to be dominated by more alkaline mineralogy. Subsequent to that, then, we have the effect of precipitation. And obviously, rainwater contains dissolved carbonic acid, which therefore goes into the soil, disassociates, releasing that hydrogen. And it can have tremendous effects if you're in very humid climates that have high rainfall activity. And generally speaking, if we get into alkaline climates, rainfall is limited. There's limited amount of carbonic acid coming into the system, and it does. But the key reactions here we have are that for CO2 going into the water phase and releasing hydrogen. But as that pH falls, there's a secondary reaction where aluminum reacts with water, and we have a release of three protons in the system. Now, that aluminum can be a really big factor, but it doesn't really happen until the pHs get very acidic. So for a salt pH, that value is right around a pH of 5. This is a data set that we have here that I picked up from a project in California back in 2005. And you can see here that once you fall below a salt pH of 5, that acidity climbs exponentially. And you can see rapidly that, at 4.5, between 4 and 4.5, you can reach soils that have 150, 200 parts per million exchangeable acidity, which makes it very difficult to reduce because it takes a lot of lime. On a water pH basis, this is about a pH of about 5.4. But this aluminum thing comes to be a very big deal because once we get into a lot of cereal grains like wheat, like corn, we're going to have a real problem with exchangeable aluminum in those systems as it becomes very acid. So let's talk briefly about those processes that contribute to acidity. I've already talked about carbonic acid that's dissolved in rainwater. Higher CO2 levels in the atmosphere create higher amounts of carbonic acid. It's very important to understand that this is how most soils have formed on the landscape over hundreds and thousands of years. Secondarily, then we have the effect of oxidation of nitrogen and sulfur, fertilizers, or anything that's associated with organic biomass. And these generate ammonium, and when they undergo oxidation, in this case nitrification or mineralization of sulfur, we're going to release a lot of protons. In the case of ammonium here, we're releasing 2 protons for every part per million ammonium that's put into the system. Third, we have organic acids. This specific decomposition of organic matter release hydrogen ions and the organic acids dissociations. Fourthly, we have atmospheric deposition of sulfate and nitrate, such as that released by volcanoes. This has been a big thing in the past, but with the removal of sulfur from coal-fired power systems, that's a much less of a problem today. And then finally, we have roots, because roots, in order to take up cations, release hydrogen into the rhizosphere. And so therefore, we have a mild case where root activity is actually releasing protons. So we talk about soil pH methods across North America, which measure the active acidity, where primarily one-to-one water is dominantly that system that's being used. It's being used in the Southeast from coast to coast. It's probably the oldest method out there, probably dates from about the early 1920s. Basically, the electrode 1 part soil, 1 part water. More recently, there's been a lot of interest in doing the salt pH. I could talk about that infinitum here, but the bottom line, because electrodes require ionic strength to perform the measurement, it gives you a basis of soil solutes in that system. And generally speaking, it's becoming more of a dominant system. Years ago, there was probably only a handful of labs in the United States doing that method. We're now up to, in the AOP program, we're running about 30, 35 labs. If we look at the saturated paste method, which many of you are probably not familiar with, but basically you saturate the soil with water and then immerse the electrode into the paste, that's dominantly in the western part of the United States, only because they can use that same method for measuring the, measuring the soluble salts in the soils. And then finally, we have 1 to 2 water. And believe me, there's 1 to 5 water, etc. But those are the 4 primary methods. When it comes to measuring reserve acidity, it's a whole different story. So the oldest method out there is pretty much the SMP method and the Adams-Evans method. Both of those methods came out of the late 40s, early 1950s. Dominantly, the SMP method is based on several different acids that are used to measure the buffering capacity of the hydrogen in the soil. And I'll get into that more later. The Adams-Evans was pretty much dominantly developed in the southeastern United States. The Mehlich buffer pH, the original, was developed in North Carolina. And you'll see here, one of these methods have undergone modifications in time. So for example, the more Socorro buffer pH is a modification of the Adams-Evans. It removes hazardous reagents. The same thing with the modified Mehlich pH. And then Frank Sikora, he came up with a method back at about 2003 to remove the hazardous reagents from the SMP. So basically, the Sikora is a mimic of the SMP buffer pH. It has all the basic characteristics, but it just uses different reagents to get there. We also have the Woodruff buffer, which come out of Missouri in the 1950s, and there's a modified Woodruff buffer. And then last but not least are the two newest methods out there are the Sikora 2 buffer. Frank, when he developed the Sikora buffer, he wasn't satisfied. He went back to the lab bench and did a more advanced. And really the only difference between Sikora 1 and Sikora 2 is that Sikora 2 is using U2 normal KCl basically as its primary measurement of the pH. The calcium hydroxide method is unique. It's only done at the University of Georgia. It's basically a one-shot measure pH, come back, add calcium hydroxide, you get a second data point, and you can measure the amount of reserve acidity that has been eliminated. Now, let's talk about the buffer chemistries and how they work. This is a titration curve here on the right. This was developed, provided to me by Byron Vaughn when he was still at, well, it was MDS Harris when he was working there. And basically you see these multiple reagents here, TEA, p-nitrophenol, potassium chromate, calcium acetate here. They form the basis of the reagents in that SMP. Each has a different pKa. So basically you mix it with the soil and each one of these buffers will kick in at a different pH. And you can then quantify the amount of reserve acidity in that soil. The bottom line is it's buffered to 7.5. So any depression in that buffer pH from 7.5 is giving you a degree of amount of soil acidity in the system. Okay. And all these buffers, Adams-Evans, Mehlich, Sikora, they all work the same way. They just use a different set of chemicals to measure the amount of reserve acidity in the system. And as I said earlier, the Sikora buffer is basically a mimic of the SMP. Now, I'm not going to go into all the chemistry of all these, but I just picked out 4 dominant methods here. So here's your SMP. Here's the reagents and their concentrations in there. Highlighted in red are those materials that are considered hazardous reagents. P-nitrophenol, the MSD, has a data sheet on that, is pretty nasty stuff. The same thing goes with potassium dichromate. You'll see all these here have different compounds in them, but they all have at the very top of the list a very heavy concentration of salt. In the case of SMP, it's calcium chloride. In the case of Sikora buffer, it's potassium chloride at 2 normal concentrations. Adams-Evans is 1 normal. Mehlich there, it's using, excuse me, it's using calcium chloride. They all focus on using a large amount of cation concentrations in them to kick off that reserve acidity off the clays. Here you see SMP is buffered at 7.5, Sikora at 7.7, Adams-Evans at 8, and the Mehlich at 6.6. Any depression is, when you mix that with the soil, any depression in that pH value will tell you that there's a degree of acidity in that sample. Now, just real briefly here, I've got 2 graphs here on the right. These are correlations between these methods. This is from the ALP database. There's 173 soils on each one of these graphs. You can see here SMP versus Sikora buffer, pretty linear relationship. I mean, Frank designed it to be a 1-to-1. It's not quite 1-to-1. Sorry, I have to move my listing here of people that are on the line here so I can tell you this. It's R-square 0.9 on this database. Frank says it's 0.1, but a pretty good R-square. If we look at that versus the SMP versus Adams-Evans, again, a pretty good relationship, but it's basically half of that of what the SMP is. In other words, it's 50%. And you'll also notice it's a pretty tight range. That SMP buffer, you look at these soils, basically the entire linear range is only from pH 7 to pH 8 on that buffer. So it becomes very tight to determine. It's a very shallow slope. So you can measure, you have to measure very precisely. You need that 3 significant digits in order to do that. Okay, that's not working. Sorry. So 2 more correlations. This is Socorro against the Woodruff buffer. Basically, it says Woodruff buffer, so 3/4 that of a Socorro buffer. And down below there at the bottom is Socorro versus the Malik. And again, all have pretty good correlations between one another. The big thing that changes is the slope and the intercept on these. And bottom line is we don't really get into this too much because each one of these buffers are worked in a different region of the United States. The Adams-Evans is still used extensively on the East Coast. The Malik buffer is pretty much limited to the East Coast as well, but different set of labs. North Carolina, Penn State, Maine, and a couple of the other land-grant universities have moved to the, when I say Malik, it's truly the modified Malik because they've removed the barium chloride from the original method. So now, one of the things I like to look at in a data set is relationships. And so here we have the salt pH versus the Socorro buffer pH. And this is again for the 173 soils out of the ALP database. And when you look at this graph for just a second, you see we have acidity down there measured at active acidity, and then on the vertical we have the reserve acidity. And if you'll notice, it forms a really nice triangle there because once we're down below soils that are above 7 or 7.5, there's no reserve acidity, but it explodes as we go down in acidity down onto the left. And I've marked in here where that exchangeable aluminum comes in here around pH of 5. But you see this parallel diagram now where you have boundaries. There's really no soils in our database that fall below that, say it's a pH of 5.5 and a buffer pH of 6. It just doesn't happen. And conversely, you have those at the upper side. Now, obviously, as we move to the right, to the left, and we move down, we're starting to see soils that have higher clay contents and higher organic matters. And also, when we get below 5, we're dealing with large levels of exchangeable aluminum going on. Now, if we parse this data set just a little more, we sort this data set based on organic matter, just organic matter alone. And I've sorted this based on 5 concentrations of organic matter. So we have those that are in white that are 0.1 to 2%. And if you'll notice, they're dominantly at the top of that curve. In fact, there's several soils there that have very acid soils, but have buffer pHs exceeding 7. If you look at those soils, this 90% of those soils exist in that range. Okay, and have buffer pHs less than 6.8. Whereas 65% of the soils that have more than 4% organic matter have buffer pHs less than 6.5, which tells us that there's a lot of reserve acidity in those higher organic soils. It's really quite interesting to look at this because organic matter is like the first sort that you can see on what you have going on with reserve acidity here. We always talk about clay content being important, and believe me, it is, but it's also the type of clay. But truly, organic matter across this particular data set is more indicative of telling us how much reserve acidity than what just would be with texture. Now, I love to pile into data and do data analysis. And some of you may know that I've done some multilinear regression work where I start looking at these variables that affect buffer pH. Now, the model at the right is a multilinear model that only uses organic matter and pH exchangeable aluminum to determine the relationship between a predicted Socorro buffer and a measured Socorro buffer. And it's quite astonishing if I just use those 2 variables on the ALP data set of 173 soils, and remember, these go from 3.9 to 6.69 on pH, we see an extremely tight relationships, and that, R squares of 93 point or 0.93 are pretty astounding, and that most of the values are within 0.12 pH units of the measured value on the model. There's only a 1, 2, 3, 4, 5, 6 data points that fall outside those 95% confidence levels. Truly goes to show you that we could probably estimate the reserve acidity if we just know, in this case, organic matter and KCl extractable aluminum. Okay, so sorry, I have to turn my mouse wheel here to advance. Soil pH calibration. All buffer methods for lime require a calibration to determine liming rates. I mean, we can talk about a buffer pH in 6.7 or 6.2, but until we know a calibration of what that is interpreted, we can't make a recommendation. So lime rates are based on a specific soil depth. Typically, it's a 0.6, 0.7 inch depth. It's based on an effective lime quality. Not all lime is created equal. Generally speaking, we use an 80%, 90% level on the exchangeable acidity or calcium carbonate equivalents. That's what ECCE stands for. And then sometimes we'll shoot for a target pH, because if we're at a pH 5.0 and a buffer pH of 6.5, it may come back that the farmer needs 7 tons of lime to the acre. Well, we'll fit in a target pH of, say, 6.0 so that he can cut his lime rate down. I mean, obviously, we rarely lime all the way back to 7. We're going to hit a window of 6.0 to 6.5, generally speaking. And then there's recommendations, adjustments for high organic matter soils. All this is based on land-grant universities, which have more than most of this data has been done over the last 70 years. In fact, rarely is any of our lime calibration data newer than 30 years. I believe Iowa State and Oregon State are the only universities who have developed any new calibration data that's less than 30 years old. And believe me, it gets kind of complicated because we have 9 lime buffer pH methods, and then, who did the work and how many soils did they do. I know Amber Moore in her last publication, I believe she did 24 soils in her data set. That's probably adequate enough to develop a good model on calibration and making the recommendations. But as if you're only working on the soils in your backyard, the calibration's only good as your backyard. So, sorry, I have to pull my wheel. I apologize for that. So let's take a look at these lime recommendations real briefly. And I'm just going to contrast here Socorro, Adams Evans, and Malik side by side here. When you look at the Socorro, we can just substitute in the SMP because there's a direct mimic of that. So the Adams Evans was developed on low CE soils of, say, the Carolinas and Georgia. It's a lot of 1-to-1 K minerals, whereas the SMP is developed on soils much higher in CECs, dominated by 2-to-1 minerals. And so look at these responsive ranges, and I have the tons per acre on each one of these on the buffer pH. And I just pulled this out of some data sets that are published online by the land-grant universities. In the case of Socorro, no limes recommended until you get below 7, and then it's 1 ton to the acre there, and it goes to 5. And when you get a buffer pH of 5.2, it's 10 tons to the acre. Remember earlier I mentioned how compressed the Adams-Evans buffer is. You can see between a pH of about 7.9 and 7.0, you go from 0 to 10 tons the acre. So you better have good precision in your lab, because you're going to need that 3rd significant digit to make your lime recommendation. And then we have the Malik over there on the far right, and you can see it really doesn't kick in till a pH of about 6.6, and then up to, if you get a buffer pH of about 5, equivalent to Socorro, it's 10 tons the acre. I want to bring this to your attention because you really have to pay attention when you look at a university's lime recommendations of what kind of scales they are working with and how each one of these buffer pH methods are quite a bit different from one another. Okay, so I mentioned earlier that it's kind of interesting what happens as we get into sandy soils. And each one of these buffer pH methods has its limitations. And so this is the same graph I showed you earlier, but I've pulled out all the soils with less than 70% sand. These are just soils that have, dominated with more than 70% sand out of the ALP database. And so these are basically sandy loam and loamy sand textures. And there's 18 soils there in that have pHs less than 6, but have buffer pHs greater than 7. And I really picked these out right here. You can see this box where none of the lime recommendations across the country for Socorro would be making lime recommendations on these soils. Yet we have pHs well below 5.5. And in the case of two of these soils, one from Nebraska and one from Indiana, they're at 4.5. Obviously have limitations. They probably have quite a bit of aluminum in there. And if you look at these soils, all but one fall in that nice grouping there, right? That last one there at the very low end happens to be a sandy loam that was collected in Rhode Island from a peach orchard. And guess what? It has 11.5% organic matter. Goes back to this point I made earlier, how important organic matter is when we start talking about the amount of reserve acidity in these soils. So my point here is the limitations. Most of these lime recommendation buffer, or most of these buffer pH methods really do not do a very good job on low CEC soils, soils dominated by sand, and specifically soils with very low organic matters. Yet they can have very significant low pH values. So how do we calibrate these? So this is a data set that I worked on back in 2006 and 2007. We had a grant in California. We had 98 soils in this data set. We did SMP, Woodruff buffer, Malick buffer, Adams Evans. We did the 4 biggies. This was actually precedent because we did the work before Socorro had come online. And we did a 5-day incubation with calcium hydroxide, okay? And so that's how we determined what our 5-day lime rate is based on an incubation. We basically took the soil, we added a given amount of lime on day 1. If we measured the pH, if it wasn't 7, we added more lime, et cetera. So it's 5 incremental days of adding lime, calcium hydroxide to the soil. And this is not a terrible R-square, 0.87. That's kind of typically what we found. The only method that wasn't correlated very well was Adams Evans, but the Malick, the Woodruff, the SMP were all very similar. So this calibration involves incubation. And what I mean by that is we're going to add lime reagents. It could be calcium carbonate, calcium hydroxide to the soil, and we're going to let it incubate under moist conditions. So we have multiple variables here. We have the temperature, we have the moisture content, we have the lime neutralizing value of the lime source we have the fineness, what's the surface area of that lime? And then you got this issue of, well, guess what? When you do incubation studies and they're under aerobic conditions, we got the potential for nitrogen mineralization. You get organic nitrogen, fertilizer nitrogen that's going to form nitrate. And when it forms nitrate, guess what happens? We're acidifying that soil sample. So a majority of our calibration data in the country is more than 70 years old. I'm kind of harping on the set on this, but it's actually, we're really standing on really old data that was done on slide rules, okay? SMP and ADIP calibrations there are newer methods out there, but what they've done is they've regressed it against the old calibration data set. So it's really not new calibration data. It's regressed on old data. Okay. So now I just pulled out 3 land-grant universities here, Wisconsin, Iowa State, and Delaware. These are tables you can look up online. This basically tells you that if you know what your buffer pH method is and you know this value, you can come up with a prediction of how much calcium carbonate it takes. And if you look here at the Iowa State, they actually give you that target pH that you want to hit based on depth, which is very nice to see because you can come up with, okay, I'm only going to lime it to this depth and I want to shoot for a 6.5 pH. It gives you that ability. Delaware, it's the Adams-Evans, again, water pH and the buffer pH, and you come up, those values there in the table are all in tons per acre of lime. And it tells you at the bottom that it's a certain quality of lime. And then up at the top is Wisconsin. Again, you have a target pH, and then you have a formula that you go into, and you have to put in the water pH and the buffer pH. In this case, it's SMP or Socorro, and it comes up and tells you that. So if you'll notice, almost all these land-grant universities, and there's about 35 of these online, you're going to look at a depth, a target pH, an adjustment, whether it's a mineral or organic soil. That's pretty limited. I think only 2 or 3 states have that. And then there's lime neutralizing value, or sometimes NV, or sometimes exchangeable calcium carbonate equivalent. I mean, everybody has their own way they looked at this and where they were decided that they would go with. But you get a good impression here that all this data is out there. You can look at it. But the question is, how good is that data? So back in 2021, just 4 years ago, I approached the first group and I said to them, well, you guys are doing a lot of great work on phosphorus and potassium. I really applaud them. It's been a monumental achievement. But lime's a big deal. So we pulled 6 soils from the ALP database, and we went to each one of the land-grant universities, and I said, given these properties, and we told them pH, the method of pH, the buffer pH method, the organic matter, the CEC, we told them all this information. We said, okay, 6-inch soil depth, 100% lime quality, ECCE. Tell me how much your lime recommendation is. And so we went to 31 universities across the United States. And this data is what we ended up for just one of the soils. This is ALP SRS 2115. This is a soil out of, I believe it's out of Indiana. And we've plotted from highest lime recommendation to the lowest lime recommendation, okay? So 31 labs, and you'll notice there at the very far right, and my windows here. So Minnesota gave us the highest lime recommendation, basically 3 tons the acre. And then you'll see the median there is about 2,000 pounds, mean is 2,100, the median's 1950 of all these labs. And there were several labs over at the very far right that had no lime recommendation for a soil pH of 5.84, a Socorro buffer 6.8. It was really quite astonishing. Now, if you'll look here, a majority of the labs are right here in the center, right around that 2,000. But there is more than a third of the labs that are over recommending limes based on their calibrations. And there are more than a third of the labs that have, well, let's say 15% of the labs are making no lime recommendations. And it's because they've all been done at different times in different places, and they calibrated in their own backyards. So this was quite astonishing to me. I mean, I knew we had issues. We've always had issues in making recommendations on potassium and phosphorus, but this was quite astonishing. It's also quite noticing all the red dot bars there, the red arrows, there are all the mid-Atlantic region. There was only one lab in the mid-Atlantic region that didn't recommend lime, where all the others are pretty close to that 2,000 pounds to the acre. So, okay. So, what the fallout of that was is 2 things. One, I brought there was really good data to bring the attention to the first group, how big an issue we have with lime, specifically our recommendations. I think the methods are all good, but the recommendations are a real problem. And number 2 is we got a publication out of that. That is under review right now, and I expect to have that published come midsummer. Okay. So the first project, they've focused on potassium and phosphorus, but they developed in January 23 a targeted goal to go after lime. And the first was identify current US pH and buffer methods and lime recommendations. And again, that's a publication now, it's in process. And we've identified those inconsistencies. Number 2 was develop grant support through industry, government, commercial interest to generate new lime recommendations, because it's going to be a big project. And then establish a multi-year research project to assess the soil acidity and generate new lime recommendations. and really focus on doing a good incubation study. And then the last one, which is off in the distance, we can see that, down the road, is develop new education programs. So the first Lyme incubation study. Well, first of all was we had to get representative soil samples from across the United States. And so our goal was to collect 120 soils across various regions, ranging in parent material, texture, cropping systems. We really want a wide distribution, and we shot the window from pH 4 to 6.5. Our current database has organic matters from 0.7 to 8.5, and we've covered from loamy sand to clay loam. So I think we've done a good job of parsing out across the country a wide range of soil materials. Our status as of yesterday, we've collected 128. So we've really exceeded our goal. We've got soil samples from 34 states. Again, loamy sand out to clay loam. That's based on GPS coordinates in which Sergo, the national database on soils, tells us it is. And we have an additional 31 soils in progress. We've missing soils from Michigan and Tennessee. So I guess we won't get any calibration data for those things. They're all in cold storage in Colorado. We have 8 to 12 kilograms of each soil. I want to really commend those people who are on the webinar who participated with us on this project and the soil collections. I got to say, I was quite amazed how many soils we got out of Maine, Vermont, and New Hampshire. I figured that would be Achilles heel for us, but we do have soils from there. On each one of these soils, we've collected metadata on GPS, depth, moisture, crop, tillage, fertilizer history as best as we can, Sergo data, the data of the submitter, and the contact information. So it's got quite a bit of background information on each one of these. The Lyme pilot study, the Lyme incubation pilot study is in progress, and we expect to finish that in April. Just to kind of give you what this pilot study is, it gets kind of involved. It's very interesting when I pull my academic colleagues together and we start hashing out how we're going to do this about, everybody's got input into it, but what can we afford to do and what's not that important? But we're going to evaluate 2 Lyme sources, 6 Lyme rates, and we're going to look at an incubation time frame. So we're going from 2 days out to 2 months. And we're going to utilize 3 different soils. So we've identified 3 soils from the ALP archive. They range from a salt pH of 4 out to 5.3. And you can see Socorro buffer is a pretty good range on that. Lyme sources are going to be calcium carbonate and calcium hydroxide. And you may ask, well, why are we doing 2 Lyme sources? I'm going to talk about that briefly in the next slide. Our Lyme rates range from 0 to 4 tons the acre. We think that kind of takes care of a scope. Maybe on that Socorro buffer at 6.14, 4 tons won't be enough, but we're going to get a nice relationship there. And then the incubation times are 4, 8, 16, 30, and 60 days on the calcium carbonate, and it's 2, 4, 8, 16, 30 days on calcium hydroxide. Calcium hydroxide will react faster, and that is one of the reasons we're including this in here. So this is why we're doing 2 sources. Calcium carbonate, if you look at the solubility of it, it's virtually insoluble in water. It's only 15 milligrams per liter. Now, think about a soil matrix. You're going to bring it to 50% water-filled pore space. That's 25% water. There's very little bit of that calcium carbonate that's ever going to go into solution. So it's going to require a longer incubation. And then you look at the solubility of calcium hydroxide, it's 1,730 milligrams per liter at 20 degrees C, and it's 115 times more active than what you're going to get with calcium carbonate. We really want to push this reaction forward faster because the longer the incubation goes, the more nitrification we're going to have, which is going to pull down the pH of what we're doing. And so it's really a way to optimize the system. So now, we're right now wrapping up the pilot study. We've had all these studies sitting in a laboratory space. We used 120 milliliter specimen cups, 100 grams of soil. We moistened each one of those soils to 50% water-filled pore space. And there at the left, or at the right, is a particular soil. It was ALP 2401 that was collected out of South Dakota. It's the 1/4 ton to the acre rate. It's under the 8-day incubation period. At the bottom here is 30-day incubations. These are both calcium carbonate and calcium hydroxide. You can see this starts to tie up a lot of space. We have to check the water in these every 72, 96 hours because we're getting a little bit of evaporation even though they're covered. The background of the photo there is humidity and the moisture content or the temperature we have in the room. We try to hold it between 24 and 26 degrees centigrade. So, it gets to be quite involved. Now, before I leave this slide, so what we're going to do is calendar date is February 14th, so the 60-day study is going to be completed. We're going to take these soils, each one of these soils, when we're done with the time frame, we dried and ground these. Then we could ship these all off to a lab, and we're going to do in triplicate, we're going to do pH, EC, nitrate concentrations, so we can get a handle on how much lime it took to create a certain pH after so many days. I anticipate that we're going to find calcium hydroxide is going to work the best in a 4 to 8 day time frame. So we feel 4 to 8 days is going to minimize the amount of nitrification that we're going to get relative to a pH or a time frame of 60 days. When we come back from this pilot study, when we're going to launch into the major study. And so bottom line is it gets pretty complicated and it's going to become the giant, the giant elephant, because it's going to be 3 pH methods on all 130 some soils, 6 buffer pH methods, EC, exchangeable aluminum, Malic 3 cations, organic matter, TOC, et cetera, et cetera. You can see we've whittled this down a lot from what we originally came to in here. But the bottom line is that all this analysis is going to be done in triplicate. Secondary and lab analyses are going to be EC, nitrate, ammonium sulfate, Malic 3 micronutrients, CEC. I don't think those are going to be as important, but we'll wait and see. The objective is 120 soils and 6 lime rates to develop a new calibration data set. Our end goal will be to have every one of the buffers that we have in the study, all 6, we'll have calibration data for all these soils across the United States. And you know what? We're going to set the data set up so that if we want to, we can say, well, I only want to pull the soils that came out of Iowa and Minnesota, or I only want to pull out the soils from the West Coast. We'll have the capability to look at the model anywhere in the United States where we collected soils. We also intend to do a set of validation soils that will be new collections that we're going to go into. My last point, and this is the reason I got involved in this project, was I really don't think we need to run buffer pHs anymore. I believe that we can come up with predictive models. It could be 2 variables. It could be 5 variables based on the analysis of those listed in the primary lab analyses that we can predict what our buffer pH is. So, okay, in summary, acid soils are extensive in the US. You don't realize this, but 20% of the soils going through labs in California are acid soils, whereas if I'm in North Carolina, like 80% of the soils are acid. It's a big deal. In 2018, that was valued at a $3.3 billion industry in terms of ag lime. We've really got good at measuring soil pHs and the buffers we have, but we have so many methods, and we've taken a big step. We've removed the hazardous reagents for SMP and Adams-Evans, but it's a lot of work doing these. And the worst thing of all is that we have calibration data that comes from all the land-grant universities that's over 4 decades old. And hopefully this first project's going to develop new recommendations, and we'll be able to look at these exclusively by region or by method. And then now it's time to answer the quiz, and I want to see how well you all did. So soil buffer pH is a measure of exchangeable, or sometimes called reserve acidity. A factor which increases soil acidity is ammonia-based nitrogen fertilizers. For every 100 pounds of ammonium-based fertilizer that goes on a farmer's field, you're looking at 200 pounds of equivalent lime it takes to neutralize the acidity it generates. Soil buffer pH, lime recommendations require, the answer is calibration. You can't move forward unless you know what methods have been calibrated. And then lastly, soil properties, that are correlated with lower soil buffer pH is organic matter. And I think I showed that very dramatically in that one slide of the ALP database. So with that, I'm going to take time for questions. Corey? There you go. Hello, somebody talk?
Sorry, I was muted.
Thank you.
So before we move to questions, I do want to remind everyone that there is an opportunity for CEAs to earn CEUs from this presentation. The best way to do that is to hit the QR code provided on the screen right now and show that you were on the presentation. And with that, I think we do have a couple really good questions in the chat, Bob. And so we're going to start there. If any other questions come up, feel free to raise your hand if you want to ask a question live. Otherwise, just put questions in the chat. And so, Bob, our first question, Jared asked, for calibrations, do you measure S&P buffer before and after the incubation or both ends of the incubation?
For the calibrations, we're not going to measure it after we're done incubating, because what we're going to measure is the change in pH with a given amount of lime on each one of those 130 some soils. So the idea is that we'll look at that, and you know, once we start to see pHs over 6.2, your amount of active acidity that's left is really very small. Now, I will parse that on saying that if I have a high organic matter soil, it probably still substantial. But the bottom line is what's our target pH, right? You know, we get into soils that are very acid, have a lot of exchangeable aluminum. Economically, you can't afford to put on the lime requirement. So you're going to look for a target pH. And the goal of that program will be to find out how much lime it takes to get to a target pH.
Great answer. So just continuing through here, I think this was a really good question. Jim asked, in the LGU comparison, did they all have the same crop in target pH?
Okay. So when you get into across the country, it's kind of hard to put in a specific crop. So what we did when we told them this, we just said, hey, we want to neutralize the acidity. We're not going to talk about specifics because obviously blueberries is going to be, well, blueberries aren't going to take any lime, but the bottom line, alfalfa is probably going to be different than corn. And we tried to steer them towards cereals, but that was all we did.
So do you believe how much would that have impacted kind of those results, Bob?
You know, most of these land grant universities, and I say all but one, all you basically shoot for a target pH of, you know, whatever it was. We all saw it for target pHs of 7, and that's how we looked at it. So it was how much acidity, how much lime it took to neutralize all the acidity to bring it to a pH 7 at a given depth. In that case, was 6 inches, and it was 100% calcium carbonate. Yeah, I know we're locking the system down, but there's so many variables there. It was the best way to generate the data.
All right, great. And so next question, doesn't the lime recommendation depend on the crop being grown and its an ideal soils pH, or are lime recommendations standardized based on a target pH, e.g. 7? So you kind of already answered that, but do you want to
I'll just say this. I think a lot of the recommendations of the universities, not all, but most of them are designed around a target pH.
So next question. So how do you incorporate the effect of temporal and spatial variability in soil pH into a lime recommendation?
Well, okay. I'm gonna play a game here with this because it all depends when that soil sample was collected, right? I can tell you that if I collect a soil sample in the fall, I may get a slightly different pH and that value in the spring. The VRT stuff on spatial variability across landscape, that's a whole different issue, okay? But the spatial or the temporal differences that we have with pH and time, you know, it's all when the soil sample was collected. And then I can tell you that if you get on a very loamy sand texture, low organic matter, and you sample it in the fall, and then subsequent to that, they put on fall anhydrous at 300 pounds of the acre, you could have a wildly different pH in the spring. because nitrification is going on, and it has very low buffering capacity. So it's going to pull down the pH. I mean, we have all these issues in agriculture about soil sampling time and the crop and all this. My whole point behind this whole thing is this. Uh, we got to have better calibration data for what we have for the soil samples that come to the lab, period. And that's what the goal behind the First Line project is.
All right, great answer. So we're getting some new ones in the chat. Moving down. I find this really interesting because I think in the US we don't think a lot about pH calcium, but what about pH calcium? Is it better than pH water to measure soil salinity? Any thoughts on that? What about soil having pH calcium more than 7 that lies in the range of 7 to 8.5?
I'm not fully understanding the question. pH calcium. When we talk the log of the calcium concentration?
I guess maybe I'm misinterpreting it. It says pHCA. That's how I would read that, pH calcium.
Or maybe they're talking salt pH.
Oh,
Okay, so separate presentation. Go back online. You can look at the ones that we've done in the past with Alta. I think summer of 2023, David Hardy gave a whole presentation that's on the Alta website. The bottom line is water pH is plagued by problems. And what I mean by that is the salinity, the EC of the solution, when you mix the water with the soil before you measure pH, is greatly impacted by how much salt's in that solutions. Case in point, we published a paper on this in SSAJ in 2010 with David Kissel. Basically, it says, hey, if I got a low EC soil versus a high EC soil, you can get radically different pHs. And what the case was, if a salt pH versus a water pH, it was a sandy loam out of O'Neill, Nebraska, the pH difference between the two methods was 1.4 units. And what happens is you have junction potential when you stick the electrodes into that supernate solution, you have a junction potential issue, which gives you basically an artifact. And what I mean by that is those electrodes require ions to develop the measurement of the millivolts. And if you don't have enough salts in there, you get a biased number because it's a function of the salts. The last thing I'll say is this. You want to try and measure pH in distilled water. Good luck.
all right. So I did or I guess here we do have one more question. How effective are the buffer pH tests if a field was limited to was limed, sorry, less than 3 to 5 years ago, especially under dry land conditions?
Boy, that's a really good question, because if you had a field that was in a low precipitation zone, let's say less than 20 inches per year, and it was limed 2 years ago, my guess is most of the lime's not has been used, but probably still a quarter of it's left. I mean, it's one of those things we're starting to make assumptions, right? If you were in a 30-inch precipitation zone, central Iowa, you had a wet fall and a wet spring, or at least one of those seasons wet. My guess is those lime recommendations are or those values the lime that was applied is probably pretty much been already done. Sidebar, on my own personal experience on my home farm, we're liming every 4 years, 3 to 4 years, kind of depending on what we find. We're quite surprised in that we go behind a high corn yield where we put on lots of nitrogen. Our pH values, they're nowhere close to the target that we were looking at. They're well below a half a unit, a quarter unit below from what we thought they should be at. This is one of the things people don't realize. High nitrogen environments, especially ammoniacal anhydrous urea, they really kick out a lot of hydrogen. And worst comes to worst is you got a guy who's doing corn silage, because guess what? Corn silage hauls off a lot of cations, and that doesn't give the soil a chance to recharge. And so it really perpetuates a lower pH conditions. So, one last sidebar. I'm famous for those last sidebar. I've been on fields in Northwest Iowa. Surface pH is 6.2. Subsoil pH, 4 to 6 inches, 5.0, have exchangeable aluminum. Well, where did that come from? It's been long-term no-till, 200, 250 pounds of nitrogen for the last 30 years, corn soybean rotation. Uh, the farmer refuses to put lime on because he'll have to till it in to make it work. So,
All right, I see no other questions. If someone wants to put a question in chat, we can wait a minute here. Otherwise, or again, feel free to raise your hand if you want to ask a question at this time. Oh, it looks like we came off mute. Do you want to expand on your question from earlier?
Hello, can you hear me?
Yeah, we
yes,
can hear you great.
Yes, yes. I have a question about the soil pH Ca measured in calcium chloride is
yes,
typically 0.6 to 0.8 pH units lower than pH measured in water,
yes.
providing a more accurate measure of soil solution acidity and alkalinity by reflecting the concentration of hydrogen ions. This method is often preferred for soil analysis and used in Australia, especially range from 3.6 to 8, depending on soil texture. What about this? Is this better to measure PSCA from pH water?
Yes, yes, Danish. So the problem with water pH, and I've explained that a little bit earlier, you require soluble salts to carry the electricity across the electrode potentials. And as I mentioned earlier, if you get into very low EC soils, soils with ECs 0.05, 0.1, what's happening there is there's not enough solute there to carry that electricity between the two electrodes. And so you end up with this artifact condition, whereas you're impaired by the measurements impaired by the lack of salts. And the whole point around 100th molar calcium chloride, it gives you an EC of about 2.2 decisiemens per meter, and it's a constant electrolyte. And one last point here about this is if you measure the EC of these buffers, okay, they all have ECs well over 10, sometimes in the case of 15 when you're using the Socorro buffer. I mean, that's completely different realm, but you have plenty of electrolyte there to carry the electricity across the two electrodes. So, no, I'm a firm advocate of calcium chloride. You can't stabilize the EC, so whatever you get. And the last thing I'll say is this. The University of Georgia did a evaluation of their database in their land in their soil testing lab back in it must have been 2005, 2006. And what they noticed was that the overall pH and water-based system of Georgia's soils would go down in dry years and up in wet years. And it's all a function of the amount of salts that were in the system, because in the dry years, salts accumulated in the upper profile, and wet years, hurricanes washed them down. So, okay.
So Bob, we do have one more question. Randy, I'm sorry, I don't know how I missed this in the chat, but Randy asked earlier, please comment on calculating exchangeable acidity from buffer pH and impact of percent hydrogen on determining CEC by summation. So that's a big question. So
That's a big question, Randy. That probably something we have to talk about on the phone, but I'll briefly answer it. And if you don't, call me. So the problem I have when I was putting this presentation together, and I knew this back when I did the work in California, the equations different people use for estimating the exchangeable acidity, the reserve acidity from buffers, really depends on who did the work. Penn State has an equation published online for SMP. I guess you can use it for Socorro. I got to tell you this. What I would say that the best way to do that, take one of the buffers and titrate them and figure out what the neutralizing capacity is for each pH unit and use that, because that's what I did back in 2005, because I found those equations, they were grossly off. The last one, the one that had the most problem was Adams Evans. I have yet to figure out what was a good way to estimate that exchangeable acidity. Now, the second part of your question was on CEC. Well, I got a problem with that because CEC is pH charge dependent. So as you go from pH 7 to 6 to 5, the cation exchange capacity of a soil is dropping because you have pH dependent charge both on the clays, but most importantly on the organic matter fraction. One of the things in the first line project we're planning to do is do pH measurements or do CEC measurements at 2 pHs, 7 and 5, because my data set that I have, and it's pretty limited, but it suggests that on a soil that has a CEC of 8 at a pH of 7, at 5.0, it could be 4, a 50% reduction. This is one of the things I think we've missed in our agricultural studies. Liming improves the CEC of the soil. And that's one of the things as a side project of the first line project I want to work on, finding resources to do that. Because I really think it's something we could advocate people that you can improve the CEC of the soils by adding lime. So if you got any more questions on that, Randy, get my phone number. It's online. You can find it. It's on LinkedIn.
That's it. Bob is willing to share his personal phone number, which is a very brave act on there.
On LinkedIn. It's on LinkedIn.
But also on the screen now is Bob's email, which may be a great way to contact him. And if you have any questions like that, I would encourage you to email Bob and not me, because those are complicated ones. But that said, I want to thank everyone for joining the webinar today. Hopefully we got everyone's questions answered perfectly. And I will remind everyone that the meeting was recorded, and we will share the recording out to everyone who registered, hopefully later this week, along with an invitation to join our next webinar at the end of February, which will also be Bob talking about the ALP program. So with that, I'm going to end the webinar. We're going to stop recording, hopefully.